All right, so let's do an example with our new fancy formula. So we're going to, I'll just paste the formula down. I'm going to make it bright pink so that you know that that's just the formula we're going to use. And at this point, it's just a matter of plug and chug. Maybe we could point out that the vector in here is equal to the vector, what, 2, 1, minus 1. And so it really is just use the formula. So I get A is, well, it's 2 times x minus the x coordinate, which is 5. And then I get plus B, which is a 1. I'll go ahead and write it. Y minus the y coordinate of 3, minus 1 times z minus the z coordinate of the point, which is 5, equals 0. And then typically we do want to go ahead and clean this up a little bit. So you can write this as 2x plus y minus z, just multiplying everything. And then I'll move all the constants over in my head. So I have a negative 10 here and a minus 3, so that's negative 13, and then a plus 5. I have negative 8 on this side. Take it over, and you get equals 8. And so that is the formula for the plane. All right, very good. So a couple of quick remarks. So two planes are parallel if and only if their normal vectors are parallel. And then this should somehow be obvious to you, but any two planes that are not parallel, non-parallel planes, they always intersect, and their intersection is actually a line. And then the final detail is that if you want to measure the angle between two planes, that's just the angle between their normal vectors. And so let me show you. If I have a plane here and then a plane coming out like that, the angle between them, all I have to do is compute the angle of their normal vectors. And if you think about it for a minute and even sketch, you can see why that's true. So let's do an example. Let's determine if these two planes are parallel or not. It asks if they intersect, and that's just checking whether or not they're parallel. If they are parallel, they won't intersect, otherwise they will. And so it says if they do intersect, find the angle between them. So let's do it. So here we go. I want to go ahead and write down the normal vector for the first plane. So I get n1 equals 1, 1, 1, and I get n2 equals 1, 2, 2, and you can see right away these are not constant multiples of each other. Their first components are equal, but the other two components are not equal, so they're not parallel. So we can say not parallel. And now if we want to find the equation or the angle between them, I just need to check the angle between the normal vectors. So the theta that I'm going to get, the angle between them, we saw in 10.3 was the inverse cosine of what? n1 dot n2 over the length of n1 times the length of n2. And I'll let you run the numbers here, but when you compute everything, you should come up with 5 over 3 root 3. So this is inverse cosine of 5 over 3 root 3. If you want to approximate this and switch it to degrees, you'll come up with roughly 15.8 degrees. Now, I do want to go ahead and show you in this video, sometimes you'll be asked to find an equation for the line of intersection. So these two planes, we know that they intersect. Their intersection forms a line. Let's see if we can find the equation of that line as well. We weren't asked for it, but I think this might be relevant for you for the homework. So the equation of the line of intersection, well, it all comes down to how you use the normal vectors here. So think about it with me. I've got my planes. Let me use my highlighter here. I've got this plane going this way, and then I've got this other plane. I think I can do this with highlighters. Let's see. This other plane going that way. And so if I want to find their line of intersection, let's say that it's right here. I've got, well, the line of intersection, let's draw it maybe a little bit differently. Here's one plane. Here's the other plane. I'm going to draw it like that, not vectors here, but planes. Okay, so they're intersecting like this. There's the line of intersection. So what I want you to realize is that the line of intersection lies on both planes. And so the normal vector for both planes, if you think about it, the normal vector for this plane is orthogonal to it, as is the normal vector for that plane. And so, said a different way, this line is orthogonal to both normal vectors, right? And somehow that gives you a clue on how you want to work that out. You want to go ahead and take the cross product, N1 cross N2. So N1 cross N2 is going to give you the direction vector V, and that you can use to finish the equation out. I won't actually compute that, but that's how you do it. So anytime you want to find the equation of the plane of intersection, you just compute the cross product of the normal vectors, and then that gives you the direction vector of the line of intersection. So let's stop this video here, and we'll do one more thing together. I lied to you. I'm so sorry. We're going to finish with a quick mathematical graph. So if you look at the code that I'm using ever so briefly, here's the first equation. Notice I'm using double equals. Second equation, double equals. I got my bounds on x, y, and z. The main function that I'm using in Mathematica is contour plot 3D. You can use that to plot any 3D equation. And then I wanted to include the coordinate axes, so I put both of those inside this show function. So that's how you do it. I've already graphed it. When you scroll down, there's our two planes, and you can sort of see the angle between them is what we computed. It does look like about 15.8, almost 16 degrees or so. So there you go. Now that you've seen it in Mathematica, now the video could be done.